So, when we talk about probability, okay, we look at this little diagram here, okay, which you guys have it in front of you, which is the chances of something occurring. Okay, so on the far left, it's impossible, it will never happen, doesn't matter how many chances you do, it's always going to be 0 out of whatever, 6, let's just say. An even chance, like flipping a coin, would be 1/2, all right? Certain, every time you do an experiment, whatever it might be, you're going to get the same percentage every time, which is 100%, okay? There's two types of probability. There's theoretical probability, which means what should happen, okay? So for example, what are the chances of rolling a 5 on a 6-sided die? 1 out of 6, right? That's theoretical probability. Experimental is what does happen. So say if we do 20 trials and we land on 5 times, 5 out of 20 is the experimental probability, okay? What does happen? So how we note what probability is, okay, the notation is the most important. It's with this little p in front. P, the probability of winning the lottery, for example. This little p in front means probability. How we express probability, it's either as a fraction, decimal, or percent. So anytime you see this notation, P with a parenthesis of whatever you're measuring, you have to have your answer as a fraction, decimal, or percent. The majority of the time we're going to see express the probability in reduced fraction form, okay? So pay attention to that because it might change. Outcome has to be either or. It cannot be a numerical value. If it has anything to do with probability, fraction, decimal, or percent, okay? So like we mentioned before, probability of rolling a 5, theoretically, it's 1 out of 6. It's what we already know what should happen. Experimental, if we were to roll a die 20 times, how many of those 20 times do we land on a 5? Okay, that's actually what does happen. All right, so some examples of this that we're going to express in simplified fraction. Assuming you're tossing one coin, find the probability of the following. What's the probability of landing on heads? Louise. 50%, 1/2 as a simplified fraction. What is the probability of landing on tails? Wes? 1/2, good. What is the probability of heads and tails? Assad? Heads and tails. 0, right? 0. Landing heads and tails. Okay. How about probability of heads or tails? Go ahead, Wes. 1. It's 2 out of 2, which is 1. Okay. Now, assuming you are rolling one 6-sided die, find the probability of the following, write your answer as a fraction. We're going to ignore the percentage because we don't need to do that right now. Okay? We're going to write your answer as a fraction. What is the probability of rolling a 5? Liam? 1/6. Good. What is the probability of an odd number? Danielle? 1/2. It was 3/6. Which reduces to 1/2. Okay. What is the probability of an odd or even number? Odd or even number? Danielle? 1. It's 6 out of 6, which is 1. Probability of factor of 6. Factor of 6. Rosanna? 2 out of 3, because the factors of 6 are 1, 2, 3, and 6, which is 4 out of 6, which reduces to 2/3. Okay? Then for number 3, Spotify has your playlist of 200 songs, 45 of which are Taylor Swift songs. Determine the probability of your shuffle songs playing a Taylor Swift song. Reduce the fraction as well. Louise, what was your initial fraction? Perfect. 45 out of 200, and what does that reduce to? Wes? At 40. Good. Awesome. All right. Now you guys are going to try regarding dozen cookies. All right. Out of a dozen cookies in a cookie jar, there are 9 chocolate chip, 3 sugar. Determine the following probabilities. Leave all answers as simplified fraction form. So a dozen is how many cookies? 12. Good. Okay. 12 in total. Find the probability of choosing a chocolate chip. Cece. 3 out of 4. We got 9 out of 12, which is 3 out of 4. Awesome. Good job. Then suppose that your friend selects a cookie before you and chooses a chocolate chip cookie and eats it. Now calculate the probability of choosing a chocolate chip. Louise. Perfect. Why is it 8 out of 11? Good. So 1 chocolate chip is eaten, or we didn't replace it. So we have our denominator changes as well as the total number. Okay. This leads us into the next piece, which is determining if 2 events are independent or dependent. Okay. If 2 events are independent, okay, the outcome of one event does not affect the outcome of the other. Okay. Dependent events, the outcome of one event does affect the outcome of another. So, looking at our previous example, for B, would this be a dependent event? Yeah, your friend and then you, right? 2 separate events happening, but 1 cookie was chosen and eaten, was not replaced, so therefore it was dependent events. So if we look at this first example, the marching band is holding a raffle at a football game with 2 prizes. After the first ticket is pulled out and the winner is determined, the ticket is taped to the prize. The next ticket is pulled out to determine the winner of the second prize. So event 1 is winning the first. Event 2 is winning the second. Would this be independent or dependent? Do you know? Why? Perfect. Good. It's dependent because after someone wins the first, they're already taken out in order to win the second. They can't win the second. All right, good. Awesome. And the next one here. You are choosing a marble from a jar. There are 6 red marbles, 4 blue, 3 green, and 3 purple. Each time you select a marble, you look at the color and then put it back in the jar. Wes? Why? Perfect. Okay. It is independent. Keyword is, or words, I'm actually going to change it. You are replacing it, meaning you're putting it back in. Okay? Replacement. Put back in to the jar to make it independent. Okay? Try the next 2, 3 and 4. All right. So for number 3, event A, picking up an ace in a standard deck, replacing the card in the deck, then picking a king. What would this be? Nolan? Independent, why? Why would it be independent? Replacing. Okay, good. How many of you did get that for 3? Awesome. 4, event A, earning first place in a track meet. Event B, earning second. What would it be? Liam? Dependent. Good. Good. Okay. So if you have, because we already determined if events are independent, then we can figure out the following probability. Okay? These are important to remember and to note. Okay? If you wanted to find the probability of event A and event B occurring, you would multiply the 2 events. Okay? If you wanted to find the probability of event A and event B, you would multiply. If you wanted to find the probability of event A or event B occurring, you would add, which someone was doing before. Okay? So if there are 2 independent events and you want to find the probability of either them both occurring or event A or event B occurring, you could either multiply or add. Okay? So if we look at example 1, we first have to determine if they're independent or dependent. Given you are rolling 2 6-sided dice at a time, determine the following. Is that independent or dependent? Danielle? Good. Okay. So since they are independent, what is the probability of rolling a 2 on die 1 or rolling a 4 on die 2? So are we adding or multiplying? Wes? Okay. So what is the probability of rolling a 2? Liam?
1 in 6.
1 in 6. Plus, what is the probability of rolling a 4? Yep. 1 in 6. So when we add 2 6, which reduces to 1/3. Okay? What is the probability of rolling a 2 on die 1 and rolling a 4? So instead of adding, what are we doing? Go ahead. Multiplying. So it's the same scenario above. However, keyword and, we are multiplying. What do we end up getting? Go ahead. 1/36. Good. Okay. So far, any questions of those 2? Okay. Yeah. Then there's something else that we would do. You would subtract, there would be subtraction involved where it's occurring in both sort of thing, which we'll get to. Actually, you'll see at the end of this. Okay? Great question, though. What is the probability of an odd number on a die, on die 1, or rolling a 6 on die 2? So are we adding or multiplying? Adding, okay. So we are adding. What is the probability of rolling an odd number? Brayden. Okay, I'm going to keep it as is for now, 36, which is right. And rolling a 6 on die 2. Yeah, Wes. 1 6. And the reason I kept it that way is because when we're adding, what do we need? Same denominator, right? So we have 4 6, which is 2/3. Okay? Now, if we change that to rolling a factor of 4 on die 1 and rolling a factor of 4 on die 2. So are we multiplying or adding? Assad? Multiplying. What is the probability of rolling a factor of 4? Yep. 3 out of 6, good. So we have 3 out of 6 twice. What do we end up getting here? Yep. 1/4, good. If you guys haven't done so already, try example 2. Okay, go ahead. All right, so you're choosing marbles from a jar, putting them back in after each pick. There are 6 red, 4 blue, 3 green, 3 purple. How many in total? You guys know. How many? Yours? 16. Good. Total is 16. Good. So what is the probability of selecting red marble first and selecting green marble second? So how did we set this up? What did this look like? Liam?
6 over 16 for the red marbles.
Mm-hmm.
Times 3 over 16 for the
Excellent. Okay, and we should have gotten, once all said and done, 9 over 128. Your reduced fraction eventually. Okay, good. All right, now we're looking at B. What is the probability of selecting a blue marble first or selecting a purple marble second? What would this look like? Paris? Perfect. So we got 7 over 16. Excellent. Good. And then what is the probability of selecting a blue 3 times in a row? So what are we doing here? Louise? Multiply. Okay, so selecting a blue was 4 out of 16. And obviously, are we adding or subtracting, multiplying? Sorry, multiplying, you said. But 4 over 16 can't be reduced. 1 over 4, 1 over 4. What was our final answer? Sawyer? 1 over 64. Excellent. How many of you did get all 3 of those correct? Good. Good job. All right. So now we talked about independent, right? So now if we look at if something is dependent, okay? If something is dependent, you guys are going to be writing in words. I'm going to tell you in words, okay? Because it's going to get very messy to see what it looks like up here. So for dependent events, we must look at the probability that event B will occur under the condition event A has already happened. So what that looks like, this little line, okay, represents probability, whatever comes, probability of B, given that A has already occurred. So if you were given this notation, A is your first event, so that has already happened. B is what you're looking for, okay? So A is your first event, B is what you're looking for, okay? So when thinking of dependent events, we think about how the total or denominator changes, all right? So if we look at this first one here, a drawer contains 10 masks, 3 black, 3 pattern, 2 bright, 2 white. Okay, every day during the first week of school, you wear a mask and then put it in the wash to be cleaned. All right, so here's the notation and here's what it means. Probability of selecting a pattern mask given that you have already selected a white mask. Okay, so you're writing this down in words. Probability of selecting a pattern mask given you have already picked or chosen a white mask or worn white mask. Probability of selecting a pattern mask given you have already selected a white mask. So where it says write in words, that's what you guys are jotting down. Okay. Okay. So we have 10 masks in total, right? Okay. We have already chosen and selected a white mask. So what is our denominator now? Addison. 9. Out of those 9, how many of them are patterned? Wes? 3. So this is our probability that says probability that you have selected a pattern mask given that you've already selected a white. So this first event, selecting a white, has already occurred. So you're subtracting 1 from the total. Okay, does that make sense? You guys okay? Are you with me? All right. Now if we look at B, there's a lot more happening. Okay? Probability of selecting a pattern mask given you have already selected a white and a pattern mask. Okay? So, what is the probability of selecting a pattern mask given you have already selected a white and a pattern mask? Yeah. Probability of selecting a pattern mask given you have already selected a white mask and a pattern mask. Okay. So you could also look at it this way with the notation. This is your last event. These are the 2 that has already occurred. So we have already chosen a white and pattern. So what is our denominator down to? Wes? 8. Out of those 8, how many patterned? Yes. 2. Good. Because we already used 1 here, and we're left with 2. Minus 1, minus 1. Are we all okay? Good, good, good. Okay. Right. Now for C. Probability of selecting a black mask given you have already selected 2 black masks. Probability of selecting a black mask given you have already selected 2 black masks. Okay. That's our answer. Sawyer. 1/8 is correct. We already selected 2 blacks, so we're down to 8. Now, out of black masks, we had 3. 2 are already selected, so we have 1 left over. Okay? The last one. Probability of selecting a white mask, given you have already selected 2 white masks. Oh, wow. Hands are quick on that one. Brayden? 0. 0 out of 8. Okay, we have no whites left. Okay, 2 white masks were already selected, so we're down to a denominator of 8. We only had 2 white masks, so we can't choose a third one. Yeah. Probability of selecting a white mask, given you have already selected 2 white masks. Okay. All right. So we just went through two different types of probability, theoretical and experimental. Okay. Then we went through probability of finding event A and event B, probability of finding event A or event B. Okay. Then we went through independent, dependent was before that. For dependent events, we use this. Okay. Now, this is just a little experiment that's going to start off our next lesson on Wednesday. Okay. So I will ask you. It's easier if I make you stand up than raising hands because we can't tell. Okay. How many do we have in total in class? You guys count. How many do we have? How many do we have? 24. Okay. That's what I thought, but. Sorry. Okay. All right. So, when I ask you these questions, I want you to stand and we're all going to count, okay? So, how many students are sophomores? If you are a sophomore, stand up, please. Oh, geez, Louise. Who's got my counting? Rosa, no. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 for sophomores. You may sit down. Okay. If you are a Warner House student, who's your counselor? You're a Warner House girlfriend. You better figure that out. Okay. If you are a Warner House student, okay, stand up, please. It's okay. 1, 2, 3, 4, 5, 6, 7, 8. Oh, really? Okay. Okay. How many students are both sophomores and Warner House students? 1, 2, 3, 4, 5, 6. Okay. All right. How many students are neither sophomores nor Warner House? 1, 2, 3, 4, 5. Okay. All right. How many of you guys are familiar with this lovely Venn diagram? You've seen it, probably, definitely not in math yet, but you've seen it in other courses, correct? Okay. So the two events per se we have here are what? What are the two things we've looked at? Nolan? Okay. Sophomores in Warner House. So, how many students are sophomores and Warner House students? Wes? 6. So that guy's going to go in the middle. Okay? How many are just sophomores? Just sophomores. 11. Why?
You could take away the sophomore center in Warner House.
Yep. So, 11. However, isn't this full circle representing sophomores? So we have 17 in total, right? So now we look at just Warner House students. How many are just Warner House? Addison? 2. Okay. Now, if we add these up, or how many students are neither sophomores nor Warner House? Where would that go? Yeah. Outside of the circle, but in the box. Now, I want you, before we put that there, let's add these up. 11 plus 6 is what? 17 plus 2? 19. And then if we add 5, what do we have? Does that represent everybody in class? Yes. So that's how you fill out a Venn diagram. Okay? what it does is if we kept this as 17, it will double count. I would add an additional 6. So we have to subtract. Does that make sense? Okay. So if I wanted to know the probability, which has to be expressed as a fraction, decimal or percent, we're just going to keep it as fraction. If we reduce it, we'll reduce it later. Okay. What is the probability of selecting a Warner student? Nolan. 8 out of 24, which we could reduce, but we'll do it later. Okay. What is the probability of selecting a student who is a sophomore who is not a Warner House student? Wes? 11 out of 24. Good. Probability of selecting a student who is neither a sophomore or a Warner House student. Assad? Good. Awesome. Okay. So what we just did, that little experiment, is a good piece to where we stop today, because that's going to intro what the next lesson is going to be, okay, which is interpreting Venn diagrams, filling them out, and all that good stuff. All right. But this worked better than the last class by having you guys stand up. You could visually see what it's like. All right. So what I'm going to hand out to you is your practice.